Hey everyone, and welcome to Chapter 7, Software Engineering. This is one of my favorite chapters. It's something that is very near and dear to my heart, and I just love this whole process because you really are seeing some type of project dealing with computer science from cradle to the grave, and I just love seeing that overall picture of what's going on and all the little intermediary steps that go on in between. So for chapter 7, we are going through all 9. They are fairly short because even though we have 9 sections in this, we only have about 30 slides or so. So please don't get overwhelmed by doing 1 through 9. First thing off is that software engineering, it's a discipline all to its own. It's very distinct from other engineering disciplines, okay? So when we talk about software engineering, we're talking about the entire process of creating software. And it's going to be from conception to approval to programming to implementation to maintenance. It's the entire cycle of that is called software engineering. It is, again, distinct from other engineering fields. There are no fabricated components. There's not a lot of intermediary parts. And a big issue with software engineering is that there is a lack of metrics. It's very hard to measure. We'll show a few of the different ways that we implement checks and at various different points, but we can't measure like a throughput like you can with a manufacturing company or things like that. There are practitioners versus theoreticians, theory people. How's that? So you can go on the theoretical side, you can go on the practical implementation side. There are tons of professional organizations here and out there to assist you in software engineering with codes of ethics and standards, things like IEEE you may have heard of, or ACM. Um, each different discipline within engineering or within the computer science field has their own professional organizations that contribute. In computer programming and the whole, software engineering life cycle, there are tools that are available out there that either can be for general program management or specific to software engineering. We call these CASE tools for computer aided software engineering, CASE tools. So typically these tools will include several different aspects. There might be project planning. So you might have calendars and planning tools and manpower. You will have project management tools in there. There will be documentation tools. Documentation is a large part of your software engineering. Prototyping and simulation, interface design and programming. You can have case tools which incorporate all of these, a few of them. You can have a case tool that is only one of these. So it just depends on what is best for your organization and what works best for your development process. Now, we can't talk about software engineering without talking about the software life cycle. We've touched a little bit on life cycles. So, when we put effort into the development of software, it can make a huge difference in the end when it comes to maintenance and updating or, needing some sort of modification. If you structure your software in a way that is easy to update and easy to add or subtract aspects of it, it just makes it easier in the long run. Unlike manufactured products, maintenance, when you look at software, you're looking at correction as well as updating as well as implementation of new features. Okay, if you have a manufactured product, it's a widget and it's always a widget. And typically, if you're going to make a new widget or correct it or update it, you give it a whole new part number and it becomes a whole new widget. When you look at software, though, what you're going to be doing is rolling versions and adding different features. So it's going to be slightly different. Ongoing maintenance of your software is going to require that someone can understand the program, how it was written, how it was structured, and the included documentation. So if you look here at this graphic, this shows the software lifecycle. So you've got a development phase where everything is being developed. That was terrible. Being developed, and you are doing your prototypes, and then you're creating, and it's a little bit more organic. Then you put it into use. You can see here that there is a loop between use and maintenance, and that loop is ongoing. It's never ending until you stop supporting that software. So that's what makes a software lifecycle slightly different from a manufactured product. Now, if you look at just that development phase, okay, we're out of that loop. We're going to have to look at a few different things. Might have a requirements analysis, or some kind of bullet list of what the user wants, what this program is supposed to do, but you've got to have some sort of specifications in order to start. Then after you gather all those specifications, you go into a design phase. This may or may not include coding. It can include pseudocode. It can include some drawings on paper napkins of what your user wants to see, but you're going to have bits and pieces of design without actually having the full blown out program. Then once the design is approved, you go into implementation. This is the step where you actually take all of those pictures and updates and the design and the functionality, and you actually put it into practice. So in your implementation phase, that's where your programming is going to be done. That is where you're taking it from pseudocode and putting it into a language. That's where you're taking it from a picture and putting it into a GUI. So the implementation is kind of where all those ducks are going to start to line up. Finally, after that, you will have a testing phase. This might be a beta test, it may be a select group of users, it may be an internal test, but what you want to make sure is that that software is robust, it's going to work on the hardware that you are given, and that it meets those requirements done early on in that requirement analysis. So once you get something working and it meets all the requirements, and it has gone through testing, that's when you can implement it for usage. Let's look at the requirement analysis stage just a little closer here. So you are going to need a list of requirements. They're going to be application oriented. So you are going to want to say, I need this to generate a report. I need this to calculate something. Okay. So what do you want that application to do, both in process and in algorithm kind of language? And just what do you want? Um, the next is going to be specifications. These specifications are going to be more technically oriented. Sometimes specifications can be something as simple as I want to use the company colors. I want the logo here. I want, this look and feel. It must use this database to pull from. That's when you're going to get a lot more into the details of what your requirements are going to be giving you. Your requirement might be pull the data from the database, whereas your specification would be pull the names and addresses from the employee database. You can see the difference there. Typically, there is an output from this stage. So even though we're in a design phase, we've got several stages. When you come out of the requirements analysis stage, typically what you have is some type of software requirements document. This is going to start to be basically your Bible moving forward. This is where you're going to go to get all of your questions answered. This is where you're going to go to say, this is what it needs to do and check off those boxes. But it is an agreed upon document between the user and the customer. Well, I guess your customer is your user, between you and your user. There you go. To basically put down on paper what they want. So that way there's never any, sort of miscommunications down the line. It's there, it's in paper. Again, in the design phase, you are going to look at methodologies and tools. We're going to discuss that later. And another part of that is you looking at that human interface, the psychology and ergonomics. So What is the user going to see? How are they going to work? We're going to talk a little bit more about that in depth later in this lecture. After that stage, we go into that implementation stage. We are creating that system from design. This is where you choose your language, you write your program, you create any data files, you develop any databases that are not already developed. This is where your software analyst or your programmer comes into play. This is where they shine. They're going to be given that requirements document. They're going to take that document and basically create an app or create an application or create software from those words. After that implementation stage, we do go into that testing stage. I touched on it just a little bit, but there are two things that you're looking for when you're testing. You're looking for validation and you're looking for any kind of defects. Now, validation testing, it's just confirming that you're checking those boxes in the requirements document saying, yes, it does take this as an input. Yes, it calculates this. Yes, it generates the report. Yes, the report has the following information. Defect testing, on the other hand, is a bug. If you type in something and it gives an error message, you never want to show that to your user, right? Or you want to give them something that allows them to either learn or to correct the problem. So that's what you're going to look for when you're looking for defects. At this stage, you want to use and abuse this program as much as possible. So you don't only want to look at the everyday usage of the program, you really do want to look for those outliers and those things that aren't going to occur very often, because that's where you're going to find your bugs. So say, for example, you say, enter in a number, go ahead and put in a name and let's see what happens. Those are the types of things that you're going to have to see and to make sure that it actually processes it correctly. Now, some different software engineering methodologies. There are a lot of these are very, very similar to program management methodologies if you've ever come in contact with any of those. But we've had the waterfall model, the incremental model, which the incremental model usually deals with prototyping, and you can do that in different ways where it's evolutionary versus throwaway. So it either is going to evolve and add new things to it, or you're going to say, nope, that's not it. I'm going to start over. There is something called open source development. This typically is where you put some requirements out on the internet in various forums or different groups of programmers, and they are able to assist you and or help you by adding to that code. And typically open source coding is free for anyone that wants to use it. And then finally, you do have agile methods of software engineering, just as you would in any program management. One of the big things when looking at the software engineering is the modularity of things, okay? So remember, we talked about designing your programming to be such a way that is very easy for maintenance and it is easy for functionality additions. So modularity is a key to this, okay? So you can use functions, you can use objects and components. These are just fancy words for having things contained in a way so that they're easy to update one portion of the program, and it doesn't really have a lot of effect on the overall system. So, if you want to add functionality to a menu bar, it might affect the menu bar, but it doesn't actually affect the report generation, okay? Because they would be very distinct in where they are in the code. And again, you can do that using these functions and structure charts. We're going to look at a structure chart here in a minute, and we can use them using objects. Now, we haven't really talked about objects. Objects, we have this. The higher level languages have some object-oriented paradigms, and they use collaboration diagrams. And typically an object, and I think we've touched on it just a little bit, is it contains the data and the processes, and it knows how to do things within itself, and that's why it's a self-contained object. So we can use those as well. And then finally, we can use things such as components, and we can use component architecture. So for example, if we want to do a menu bar and we want to add a save component, we can just use the save component, and if anything needs to change on the save component, you change the component and not the menu. So hopefully that gives a little bit of insight into some of those items and how we can make them modular. So we can look at this class here, for example, and we call this class a player. It has its attributes and it has its methods. So it has its data, which is the attributes, and its methods, which are the processes. So a player is going to have a skill and an endurance, and it's going to be able to serve and return a volley. Okay, so these are the processes and the data. Now your object is going to be using that player and creating multiple players because you have multiple players on a team, right? So when I talk about objects, here they use player A and player B. Player A may have a skill 1 and an endurance of 5, but they can serve and volley, where player B might have a skill of 10 and an endurance of 2. Okay, each one of your objects is going to have everything that's available in your class. Now, if you make a change to that class, all of the objects that use that class receive the change. So you can see that modularity. So say, for example, I want to add an attribute of name. I can go ahead and add name into the class, and then player A and player B will automatically have a name. So we can have interaction between objects resulting from the processes or the actions of a specific player. So here I've got two players, again, player A and player B. So player A can evaluate a serve, you know, you can have another player return a volley, so all of these processes can interact with each other. Okay, and here we've got an object called judge and an object called score. So your judge is going to update the score. So you can interact these just the way that you can interact any of the processes and or attributes of functions that are out there for us to use. But these are going to be your programmer defined functions. This right here is an example of a structure chart. And what we're saying here is we're introducing data coupling. So we have something called a control game. In the control game, we've got a serve, return, path, and a score. And you can see there's going to be interactions between all of these different processes. So in a serve, you're going to have a player that's going to have a serve. That player's ID is going to basically indicate the trajectory, because say, for example, each player has their own trajectory. So then the trajectory is going to go back to the game. You could do the same thing with compute path and update score and return. So all that's doing is showing that in this instance, your game is indicating the player ID, then the player ID is indicating what the trajectory will be. So that's what all the arrows mean. Don't read too much into it. Now that was called coupling. This is called cohesion. So coupling, we can do that control coupling, which we saw in the first image, where things are being grouped together and used back and forth. And we can have that data coupling, where that player ID then goes ahead and says what the trajectory is going to be. On the other hand, we have cohesion. And in cohesion, we have two different things. We have logical and we have functional. So here in this picture, we've got each object is only locally cohesive. So it is action A is cohesive, action B is cohesive, action C is cohesive. And you can see it's within an object. So within this object, each one of these objects is functionally cohesive. Some tools that we use to look at the software engineering process from beginning to end are things like data flow diagrams or ERDs, or entity relationship diagrams like you do in databases, where you can show relationships, whether it's one-to-one, one-to-many, many-to-many, and something called a data dictionary. You can see here in this picture how this could be a data flow diagram, where patient makes payments to the processing payment system. They receive bills from the process bills section, and the hospital files kind of has an inflow outflow of patient records and updating records, both going in and out to different various processes. So these are some things that we can use in order to visualize where things need to go. We have something called unified modeling language, and you can use two different things, either a case diagram, which uses cases and actors like what's on top right here, or a class diagram, which is what's on the bottom. Now, the case diagram here, you can see there would be different actions, and that's what's going to be in the box in the center. So you've got a hospital record system. It is able to retrieve medical records, update medical records, retrieve laboratory results, update lab results, retrieve financial results or financial records, sorry, or update financial records. All of these are processes, as you can see. And then what you have is something called an actor. These are going to be the people on the outside that need to access those different processes. So you may have a nurse and a physician, and they need to either retrieve and update medical records or laboratory results. The lab technician, basically all they do is going to be updating the lab results. And you may have an administrator, which is going to work with those financial records. So you can see all the actors on the outside and the cases on the inside. Or you have a class diagram here, and you have different classes. So you have a physician class, a patient class, and a room class. So a physician is going to care for a patient, and you can see here there is that one to many. So you've got one physician caring for many different patients here. A patient is going to either occupy a room or not occupy a room, and rooms host patients. So you can see how just the classes are going to be interacting there. So you can see who needs access to be able to talk to whom. Here, this is just a very quick diagram of the one-to-one, one-to-many, many-to-many relationships. Again, this is very similar to what you find in a database, but if you have not been exposed to that, a one-to-one is exactly what it sounds like. You've got a one-to-one relationship. One person, lives in one house. One to many, on the other house, is that a house can house many people. So you've got a one house with many people in it. And then the last type that you have is a many to many. So you may have many different physicians having many different patients or something to that effect. It's a little bit less common to have the many to many. Typically, we deal more with the one to one or the one to many. A little bit easier to kind of understand. Here is an example of a class diagram, and it's going to depict what we're going to call generalizations. These generalizations are going to be descriptions of the data and the actions, because remember we talked about those classes being a data, all the data it needs and all the actions it needs. So here we've got a class called a medical record, and it's got some generalizations of a date, a patient, a doctor, and it's able to print. Okay. Now, we are able to take that medical record and expand on it. So we've got a generic medical record, and what we want to do is we want to create two specific medical records, a surgical record versus an office visit. Now, if you have an office visit, you may have a symptoms and diagnosis, and you want to print. And if you have a surgical record, you might have a surgical procedure, the hospital, and date of discharge. Then you might add a discharge patient action onto it. Now, one thing to know though is that both of these records, since they are medical records, they're already going to have everything that medical record has. So really, a surgical record is going to have date of record, patient, doctor, surgical procedure, hospital, and date of discharge for data. Whereas an office visit record is going to have date of record, patient, doctor, symptoms, and diagnosis as the data. You can see here everyone is able to have a print record, and the surgical record is going to, in addition to the print record, have a discharge patient. So this is how we can do generalizations. We can try to pick the most generalizations that everything is going to have, and then kind of create specialty classes built off of that generalization. Again, we're talking about that modularity and that ability to update and change things very easily. So here we have a sequence diagram, and this is going to be just some generic, we're back to the volleyball, a generic volley. These to me look more like your Gantt charts and things like that, if you are aware and know what those are. So we've got some swim lanes here of a loop or some interaction that we have. And again, we've got that player A, player B here, they call it self and then other player. And we've got the judge and the scores. So we've got those processes that are up there in the blue. Okay, so we've got the evaluate, serve, return volley, evaluate, return, return volley, and evaluate, return. Then on in the green, more towards the right, we've got the conditions controlling the interactive fragment. So if we are still in play, this is going to happen. Okay. If it's from the server, this is what's going to happen. If it's from the server, or if it's not from the server, this is what's going to happen. And server here, I'm meaning the person actually serving, not anything to do with IT. So here, what you're adding to it is you're adding some conditional, sorry, there's a loud bang. We're adding some conditional factors in on just the plain old actions that we had originally. So design patterns. So these are going to be well-designed templates in order to solve problems. For example, if we're going to adapt a module's interface to your current needs or to control the complexity involved when you've got so many different combinations of the same activities. A lot of this is designed in such a way that you're taking that chaos and creating a pattern out of it so that it is predictable. That's all that is. Okay, so you're going to, if you're having the same problem over and over again, you're going to implement templates in order to deal with those problems. It's inspired by the work of Christopher Alexander, and it has an architecture base to it. So that's kind of where it comes from in a building sense. Simulating a system. So when you can also simulate systems when you're going through that software engineering process. You can have structured walkthroughs where if to do A, B should happen. Each member of the design team is typically given some sort of responsibility or some sort of collaboration. So everyone's testing little pieces of it as opposed to the whole thing, because what you're doing here is a simulation. It's not an actual testing. It is a theoretical experiment. Consider it a role play. You can actually a lot of simulating systems I've seen have been done with post-it notes and or whiteboards, right? You're going to basically walk through the system and see how it should act and where you might find issues that come up. One of the last things we're going to talk about is how to ensure the robustness and the ability to minimize those bugs and fixes that need to be done. So quality assurance is definitely one of them. We've got two different kinds of glass box testing versus black box testing. That's a tongue twister. So glass box testing is a basic path testing. You know exactly where you're going. It is very transparent, and this is your typical everyday usage of your software. Black box, on the other hand, that's going to be your outliers. This is where you're going to keep using it to its extent. You want to be on those boundaries and push those boundaries and see how far they go. This is typically where you go with your beta testing because you want your users to use and abuse it as much as possible. Your users will always think of a way to break it that you never thought of. So that's usually where black box testing comes in. Documentation is also very important. So you've got user documentation, you've got system documentation, and you've got technical documents. All three of these are just as equally as important. So your user documentation is exactly for that. It is for your user. It is either printed, available online. It is for anybody that is using this software to be able to look up some answers and have quick, easy access to some help and to possibly even some tutorials. System documentation, typically this is the source code, it is design documents, it might be those requirements documents added onto that, but this is what the programmer is going to kind of come up with and see. This is the actual implementation, how you would actually do updates, where you need to install things for new features. That would be in the system documentation. Finally, you have technical documents. These are going to be available to your administrators. This is how to install it, how to customize, how to update, and how for how they can help your users. Ugh, words are hard. One of the last things, the human machine interface, it's the idea of your software is a tool which is for the convenience of humans. Okay, so just think of that. So what do? You want to make those humans happy. You want to make it ergonomic. You want to make it visually friendly. You want to be able to be easily understood with like cognitively. So for ergonomics, the physical abilities to humans, how is it easy, how easy is it, how hard is it for a human to use? Your cognitive abilities, your mental abilities, is it habits, attention? It is a design purpose that all of the windows in, when you're running Windows, all of your applications have your X in your upper right hand corner. Okay, that's a habit. The same thing, typically your file menu is always in the upper left hand corner. It's being done that way because of habit. When things are changed and moved, your users may get frustrated. They're not going to know where to find things. So those are things that you do have to keep in mind. Last but not least, we're going to talk about software ownership and liability. So a lot of times software will be given a copyright. This is going to allow the product to be released while you retain the intellectual property behind it. Okay, so you can assert your copyright in specifications, the source code, the final project, the idea. There are so many different levels that you can implement your copyright. Intellectual property, since we said that's what the copyright protects, it is what is on that back end. Remember, intellectual property is something that's not always tangible in order to hold, taste, touch, feel, scratch, sniff, smell, things like that. So you've got things such as software licenses, which is a legal agreement granting user specific permission to use, but you're not giving them the ownership. So if you have a software license for Microsoft 365, you have every right in the world to log into 365 and use it, but you cannot make changes to it other than the updates they give you. Patents, on the other hand, in order to obtain a patent for intellectual property, you're going to have to demonstrate that it's new, it's usable, and it's not obvious to others with similar backgrounds. So we're talking within the computer science community that it's a new and different and improved idea. The process is very expensive and time consuming, copyrights much easier. So that's all I really have for this lecture on software engineering. I hope you enjoyed it. Again, like I said, I love working with software engineering cycles. So this is one of my passions. If there are any questions, comments, or concerns, please, as always, shoot me an email and I will see you next time.